So let's begin with recognizing that these are what I call force concept model problems. And they have a quick set of steps, but the idea is decide whether it's a first or a second law problem, try and draw a free body diagram that indicates all the forces acting on the object, apply an appropriate coordinate system to that model, and once you've done that, use Newton's laws to generate a set of relationships that may or may not answer your questions. They're supposed to. That's the hope. So in this problem, we have a wall and a book being pressed up against the wall. And the applied force on the book is kind of pushed on, at an angle like so. And let's say that the book has a mass of 1.5 kilograms and that the force on the book is 30 newtons at an angle of 45 degrees. And let's go one step further and say that the book is sliding up the wall at a constant speed. Okay? That's the setup for this problem. Now, I'm going to go through our set of steps, but I'm just going to kind of write them down as a reminder of what you should be asking yourself and how you should be setting up this problem. So, step one, is this a first law problem or a second law problem? What's that? What is your reasoning for saying second?
It's moving.
It is moving. And this is where we have to be careful. First law and second law differ by the idea that one of them is a system that's accelerating and one is not. Movement doesn't mean acceleration. So the fact that the book is moving up the wall isn't enough to say it's a second law problem. It has to be accelerating up the wall. Go ahead. Well, we don't know if the forces are unbalanced or not. And that's the thing, guys. The moment I said constant speed, it is a first law problem. Whether you think the forces are balanced or not, it doesn't matter what you think there. Once we said the object had a constant speed, this became a first law problem, which means the forces are balanced. You may not know that they're balanced. You may not know what all forces are acting in the system, but they are balanced, whether you like that or not. So, step two is a free body diagram, which we break this up into a couple of parts. A, you've got to deal with fundamental forces. B, you got to deal with contact forces. And C, you've got to, you have to apply a coordinate system. And D, deal with off-axis forces. All right, so that's step two. So let's do that part now. We need to create a free body diagram that matches what we're seeing here. So I'm going to draw that over here. And let's go through our list. Are there any fundamental forces acting on the book? Yeah. This one's the easy one. Be the first one to say it. So I'm going to draw a downwards arrow. Now remember, we know more things now than we did when we were just doing this on Friday. For example, we know that the book's weight is 15 newtons because the weight is mg and the mass is 1.5 and g is 10. So I know that this arrow represents a force that is going to be 15 units long. I'm saying that because you're trying to draw this to scale as best as you can. And considering that another force is 30 units long, you need to be aware that the length of the arrows needs to be considered in your drawing. Now, this is the weight. Are there any forces due to contact? Sure. I mean, there's one that's given to you. Regardless of what you want to call this, there's a 30 Newton force applied at 45 degrees. Now, be careful how you draw this in. When we talked about free body diagrams, all forces start at the dot and are drawn away from the dot. So you can't draw an arrow like this and it be okay. If you want to know how to deal with this, just push it through. That's how you deal with it. You push it through till it's on the other side. And then you'll have to work on where that angle goes. So I'm going to push it through, and I'm going to make it longer than the other force. It's at 45 degrees. This is my 30 Newton force. Now, I don't know if you guys know things, but let's see if we can work this out real quick. Trying to line this up, so give me a second. There we go. If this is 45 degrees, do you know that this has to be 45 degrees? You took geometry, you're supposed to. If you didn't, those are called vertical angles. So knowing that that's something you learned in geometry, I'm supposed to be able to rely on you to know that over here is where the 45 goes. If you didn't know that, put it in your notes now. I'm expecting you to know how to use vertical angles. That's a vertical angle. All right. Is the book in contact with any surface? What surface?
The wall.
The wall. So I need an arrow that represents a normal force. That force has to be perpendicular to the wall. That's perpendicular to the wall. I'm labeling it N for normal. Are there any other forces acting in the system? Yeah, I think friction. If the box is sliding up the wall, it's very likely there is a frictional force acting. Friction opposes one surface sliding past the other. And friction is always going to be parallel to the surface. I'm giving you information that's not on that sheet. It always opposes one surface sliding past another. And it's always going to be parallel to the surface. I mean, it's going to be perpendicular to the normal force. So if the book is sliding up the wall, what direction is friction likely going to be? Up or down? Look, that's one person saying down. There's 23 of you in the room. Tomorrow, you're going to have to do this on your own. So if you don't know the answer to the question, I'll say the things that you should be having in your notes. Again, friction opposes one surface sliding past the other. One surface sliding past the other. It's going to be parallel to the surface. So if the book is sliding up the wall, would friction be pushing the book up the wall or pushing against the book going up the wall? So when you draw this force, you want to draw it against the direction of motion. Friction is going to be downwards. Now there's two ways to draw forces that are in the same direction. You can stack the arrows like I just did, or you can place the arrows side by side, like so. I tend to favor doing it this way, so that all the forces are coming from the dot, but you will get full credit if you use either method. Some people like the stacked method more because it helps them feel the idea of balance. But I'm going to do this, because I like the idea that all the forces are acting on the object. All right, your choice. All right. We've made it to the end of our list of stuff, except for things like air resistance and buoyant force, and those aren't going to be here. They're going to be something like this. So our next job is to determine a coordinate system that we think best aligns with what we have here. So you have to make a choice. I gave you two priorities. I said that your highest priority should be to align it with the direction of the acceleration. Is the book accelerating? No. So we don't have to worry about that. Your next priority is to try and line up your coordinate system with as many forces as possible. So would it make sense for me to make this the x direction? It's lined up with one of the forces, but if I do that, the y direction would have to be this way. So does that help us out? No, I don't think so. I think this would be the worst way to do it. Because although it's lined up with one of the forces, it's not lined up with 3 other forces. So if you're going to do this, try and pick one that I think is helpful. So I think you all probably agree that drawing it this way is probably more helpful. So this is going to be the positive x direction, this is going to be the negative y direction, this is going to be the negative x direction, and this is going to be the positive y direction. Do I have any forces that are off axis? Yeah, I do. That 30 Newton force is off axis. So when you have an off axis force, you have to break it up into its components. Now, I want you to hear this out really closely. What we're about to do now is going to add arrows to your free body diagram. Do not do this in any part of your test where you're supposed to be graded on a free body diagram. So if you have to break a force up into components, do this separate. Do it someplace else on your paper. This is the end of drawing a free body diagram. So if I have to grade your free body diagram, you would stop here. But somewhere else, you might need to make a sketch of what to do with that 30 Newton force. So we're doing something additional. So this would be on a separate diagram. I got to take that 30 Newton force and break it up into its components. I clearly see a triangle here. So I'm going to draw components of that triangle. I think I've got a component in this direction and a component in this direction. Do you guys see that? Right? We've done this before. I'm going to label this one as horizontal 30 cosine 45 degrees because it's the adjacent side. And one that's far away, I'm going to label 30 sine 45 degrees because it's the opposite side. And I'm hoping you guys are in a position now where you don't have to draw sine opposite over hypotenuse and all that, that you can step along a little bit. Now, once you have broken up your force into its components, the force that you have here can disappear. You don't need it anymore. It was only there to give us our components. The components take the place of the original force. This is why you don't do this on your actual diagram that's going to be used for your free body diagram. It will say in the instructions, draw all the forces, not components, that are acting on the object. These are components. They're not the original force. They're how much each of those forces is in the x and y direction. Because that brings us to step 3. Apply Newton's laws. Net force in the x direction equals 0. Net force in the y direction equals 0. Now, we just add up all those forces and set them equal to 0. That's what it says to do. So I'm going to go through and just kind of cross off the ones as I grab them. Let's do x first. I've got 30 cosine 45. That points in the positive x direction. I've got normal. It points in the negative x direction. And that has to sum to equal 0. Those are the only ones that are pointing left and right. I'm going to go on to my next one, the y direction. I have 30 sine 45. Points upward, so it's positive. I have friction, so minus friction, because it's downwards, it's negative. And minus weight, because it's downwards, that's negative. Add up all the forces, taking into account their direction. Set them equal to 0 or ma. There, we've done it. If done correctly, your set of steps done correctly, your set of steps is just going to generate a set of relationships. We have generated a set of relationships. These are the relationships that deal with this problem. They may or may not be able to deal with step 4, which is solve the problem. When I gave this problem in second period, I told them I wanted them to find the normal force and the frictional force. Can you find the normal force and the frictional force from the information that's been given? Well, you look at your equations. Is there a way for you to solve for the normal force? I think it's pretty clear that you can, right? So if I want to solve for the normal force is right here. So I'll solve for it. 30 cosine 45 equals normal force. So normal force equals what, 21? That was pretty straightforward. Can I solve for the frictional force? Yeah, that one's going to take a little more work, right? Because I've got 30 sine 45 minus friction, but I'm going to have to substitute something in for weight. But weight is just mg. So I might have to do some substitution like that. That's why on your set of steps, there's a thing. Common substitutions you're going to have to use. This one's the most common. And m is 1.5 kilograms. It was a 1.5 kilogram book. And g is 10, acceleration of gravity. So 30 sine 45 minus f minus 1.5 times 10. Again, lots of steps. So now, yeah, you plug all that in, you solve for the frictional force. You get 6.2. I don't know, a kid's pulling on a wagon. So this isn't a quiz, it's just more notes, but I'm not going to lead this discussion. I'm going to go around and I'm going to critique you. So wagon looks like so. Handle. Let's say this is 30 degrees. Let's say this is a 20 Newton force. And let's say that the wagon is 5 kilograms. All right. Let's say that the wagon is new, has excellent bearings, so that there's no frictional force. You show that door. Serves it right being there in the bathroom. All right, I want A, find the acceleration of the system. And B, find the normal force on the wagon. If this were your quiz, all right, there's only a few minutes that we can spare for this before I have to go on to another example. But if this were your quiz tomorrow and you're looking to try and score as many points as possible, here's what I would expect you guys have done. It's going to start by drawing a free body diagram after you decide whether it's a first or a second law problem. I don't think there's a decision to be made. I'm asking for the acceleration. That probably dictates that you should be starting out as a second law problem. So we'll start that way. And can you interpret from the context clues what direction our system probably accelerates? So we agree that we're not pulling so hard on the wagon that it gets lifted off the ground. 20 newtons versus 50 newtons, right? So if it's going to accelerate, based on all the context clues, it's got to accelerate this way. Does that make perfect sense? All right. There are a series of forces acting on the system. Is there a fundamental force that acts on the wagon? Yeah. It's got a fundamental force of weight acting downwards. We know the size of this force in this problem. It's a 5 kilogram wagon. That's going to be a 50 Newton force. I'm still going to write W here, but it's a 50 Newton force. Now there's a force that's given to us, a tension. The kid's pulling on the handle of the wagon. And in drawing that force, I'm going to draw it at an angle of 30 degrees, and I'm going to intentionally make the arrow smaller than the weight. I'm not sure it's appropriate size. I'm not sure that's 20 versus 50, but it's smaller for sure. And I'm going to write 20 on it, just so I have an understanding of how big that force is. But this is a tension force. Is the wagon in contact with the ground? This is an important question. Is it in contact with the ground? Is it in contact with the surface? If it is, then there needs to be a normal force. And a normal force needs to be drawn in such a way as to be perpendicular to the surface, which means an upward force. And again, I'm drawing it less than the weight. There are two forces pulling upwards on the wagon: normal force and the tension force. So I expect these to be smaller than the downward force to demonstrate balance up and down. I don't think the wagon is accelerating off the ground. So I'm expecting there to be some balance there, and I'm going to label it N for normal. I am intentionally told there's no friction. So are there any other forces that we have not identified that are acting in this problem? I don't believe so. It's unbalanced. Is that okay? Yeah, because it's F equals ma. It's an unbalanced problem. It's supposed to be unbalanced. So in my next step, I need to apply a coordinate system that could be used to solve this problem. And I am telling you, your highest priority is to align that coordinate system with the direction of the acceleration. Accelerating to the right, I'm going to draw a coordinate system that is also horizontal. And I'm going to make the right the positive x direction. That means that the y direction will be up and down. It doesn't really matter if I make up positive or negative, but I'll just be consistent with what we've been doing. I've drawn a coordinate system that is consistent with my problem and uses my priorities. Do I have any off-axis forces that have to be handled? Sure do. So let's handle our off-axis force. This angle is 30 degrees. So I'm going to need two vectors that can replace the clear and obvious off-axis vector. So that's going to be an arrow in this direction. I'm just wrapping a triangle around the angle, just like we did in our last unit. The up and down one's going to go with the opposite side, so that's going to be 20 sine 30. And the horizontal one is the adjacent side, so that's going to be 20 cosine 30. Now again, we have added two arrows, but we didn't actually add forces. Those two forces take the place of that tension force, which is why when you start dealing with components, draw a separate picture. But now I can apply Newton's laws: net force in the x direction and net force in the y direction. I've intentionally made the x direction the direction of the acceleration. So it's ma. And the net force in the y direction gets 0. Do what the law says to do. Add up all the forces in the x direction, set it equal to ma. 20 cosine 30 equals ma. Add up all the forces in the y direction, set them equal to 0. Normal plus 20 sine 30 minus weight equals 0. That's what Newton's laws give you. They generate relationships. At the end, that's what you have. You may or may not be able to use just that to solve your problem. I think I'm going to be able to use this to solve my problem, but I'm probably going to have to do a substitution. I'm probably going to have to do something with W here. So, but I mean, right now, I can just plug the numbers in here and get my answer for acceleration. That's pretty straightforward. So I get my 20 cosine 30 equals 5a. Work that through and find out what the acceleration is. Here, n plus 20 sine 30 minus mg, 5 times 10 equals 0. Yeah, I can solve that for normal force. That's where you get your 40 newtons and your 3.5 meters per second squared. Yep.
So why would the y be set to 0 but not the x?
The wagon is accelerating, so we chose we said that this has to be a second law problem. When we picked our coordinate system, we forced one of the dimensions to be in the direction of the acceleration so that the other one would be 0. Does that make sense? Okay. So my car is traveling to the right. Thus, in the original picture, there's little lines there to indicate the car's direction of motion. It's accelerating at 1.5 meters per second squared. So the car is already moving to the right, and now it's accelerating at 1.5 meters per second squared. In order to do that, the engine has to supply a force of 2,500 newtons. I'd like you to find how much resistive force must be acting on the car. I'd also like you to find the net force acting on the car. So A, find the resistive force. And B, find the net force. I want to add something real quick. This question, when you see this question, you don't have to do this entire procedure. When you see the question, what is the net force? Net force, by definition, is either 0 or ma. It is the sum of all the forces. But if you have the acceleration and the mass, then you have the net force acting on the car. The net force here is 1,800 newtons. It is 1,200 times 1.5. You do not have to do that series of steps. You do not have to do all that work. Net force is either 0 or ma. That is Newton's first and second law. Now, if you weren't given these two things, you might need to add up all the forces. That might be true. But when you see the word net force, be aware you're being asked a different question. It may not require all that huge number of steps. All right, work it out, but the resistive force is 700 newtons to the left.